One, two.
Yeah, it's been two. Okay, we'll disengage it.
One.
Good afternoon. Just before we start today's seminar, just please be aware of the exit signs in case we need to leave the room for any reason, etc. And also restrooms are by the I Street side on the south side of the lobby. So also though, most importantly, those are on the internet. For those that are interested in sending in questions for the Q&A, we really encourage you to send them at first opportunity so we can have time on the air to take them. So with that, Dr. Vance.
Hello, it's my pleasure to introduce Jochen Stutz, who's the department chair at the University of California at Los Angeles, and he's the chair of Department of Atmospheric and Oceanic Sciences. Jochen's group studies chemical and meteorological processes that govern tropospheric composition, and he's been involved in many large-scale studies in this area. His group is also involved in developing and using novel remote sensing instruments to study air quality and pollutants. And he's published over 100 articles in this area. Today, Jochen will be talking about some interesting and novel measurements that were made from Mount Wilson that overlooks the South Coast Air Basin. And he'll be describing some measurements of ozone precursors, as well as several greenhouse gases. With that, I'd like to welcome Jochen Stutz.
Thank you, William, for the kind introduction, and thank you, William and Eileen, for the opportunity to speak here. Let me first say a couple of words. This was a truly collaborative effort between my group at UCLA and Stan Sanders' group at JPL, and you're going to see this throughout the talk. And I also really want to point out that neither Stan or I did actually all the work. So the two names that are underlined, Ross Chung, he's a graduate student in my group, did most of the work that I'm going to show you, and Claire Wong, who's actually also in the audience, did a lot of the work in the second part of the talk on the greenhouse gas emissions. So I just want to acknowledge the folks that actually did most of what I'm going to talk about. the topics we're going to cover today are probably the most challenging environmental topics that LA, California, and the world probably faces today. One we've been dealing with for many, many years. The other one have been dealing with for less time, but it's even more urgent. And the first one really is urban air quality, and it's very well known that Los Angeles and the South Coast Air Basin has been fighting with this for many years. And we're still fighting this battle of getting ozone levels below the federal air quality standard. At the same time, in recent years, there's been another challenge, that's climate change, and everybody here is aware of AB 32, the law by the state that mandates reductions of greenhouse gas emissions. And so this is kind of the second part of this talk, is how can we quantify or measure this effect. So while these seem to be two very different topics, you'll see that there is a common theme in this presentation, and the question really is, how do you best quantify or measure ozone precursors and greenhouse gases in an urban area? And there's quite some similarities in an urban area. The emissions, for example, from CO2 and NOx are mostly combustion sources, traffic, power plants. Then the emissions of methane, VOC, methane coming from landfills, a little bit wastewater treatment, and gas leakage, and then we have VOC emissions also from traffic. And all of those happen in this urban area pretty much interdispersed. For the greenhouse gases, the measurement is fairly straightforward. For ozone, you have to actually do chemistry in between, because while you're emitting NOx and VOC, as we all know, the oxidation chemistry in the atmosphere in the end leads to the formation of ozone, so it's not just enough to know how much precursors are there, you actually also need to understand the chemistry, and I'll get back to that. So the question really is, how do we measure these effects? How do we quantify these effects in an urban area? And the common approach is that we place a large number of surface stations in the South Coast Air Basin, for example, or other urban areas to measure the surface concentrations of these gases. And this is a very well-established approach for urban air quality, much less so for greenhouse gases, but there are still some challenges with this monitoring approach. And one of these is that these ground stations, even if you have a lot of them, only have a limited spatial distribution. They can be heavily impacted by local influences, sometimes not by design. Cities change and grow, and if your air monitoring station doesn't work, you suddenly find yourself near a source. And so how can we deal with this problem? One option would be satellite measurements, but we're not really there yet that satellite measurements can take over. For urban air chemistry, we usually get only one measurement per day in a good time period. Greenhouse gases at the moment with the new OCO instrument, it's even less frequent. So that's a real challenge. Another challenge is that the surface stations only give you information near the surface. So you don't actually know what's going on above your head. And that may be, sometimes it's really challenging when you do emission ratios because everything's modulated by metrology. So having vertical information actually can be quite useful to interpret the data. And I mentioned sparseness of monitoring data, and I think you guys will all agree that for greenhouse gas emission, sparse means really very, very sparse. There's very few stations, for example, in the South Coast Basin that measure CO2 and methane, and there's too few to really cover the entire basin. So the motivation for our project was really, can we develop methods that address this problem for the South Coast Air Basin, that we can get good spatial and temporal resolution for greenhouse gas and ozone precursors. And the idea, I put this in a little cartoon, is actually quite simple. If you can sit on top of a vantage point, like a high mountain, and look down with remote sensing instrument and measure the trace gas concentration in your urban area by using these remote sensing tools and scanning them over the remote area, you can accomplish a fairly broad spatial coverage while at the same time getting the temporal resolution you need. And that is pretty much what we did in this project. We deployed two types of instruments at Mount Wilson, which is at the edge of the LA Basin. I'll show you a map in a second. One is a UV visible multi-axis differential absorption spectrometer, and that mostly measures ozone precursors. And the second one is a new near-IR Fourier Transform Spectroscopy instrument that measures greenhouse gases and CO. And one of the advantages of this method, as you can see here, is that you can actually penetrate the entire boundary layer. So what you're going to get is something like a height average, an average over the extent of the atmosphere, and that's actually quite beneficial, especially when you do when you try to determine emission rates. Just to give you an idea, these are some pictures from the California Laboratory of Atmospheric and Remote Sensing. It's operated by and owned by JPL, and it sits on Mount Wilson, and the map on the right, shows you where Mount Wilson is with respect to the basin, and it's really right at the edge. The mountains in the LA basin are pretty steep, so to get at a high vantage point, you don't have to go far away from the basin. And it has a little trailer with a dome, which has the pointing optics of the near-IR FTS system in it. You can't see the MAX-DOAS system, it's behind the dome. And there's also an in situ greenhouse gas monitoring station here that is operated by the ARB. There's some meteorological measurements. And one of the purposes of this station from a JPL point of view is really it serves as a test bed also for current and future geostationary satellites that are being developed. And there is the experience from this project hopefully will also feed over to these future satellite missions that could help analyze greenhouse gases and ozone precursors. So I'm going to talk first about the multi-axis DOAS system. This is a system that was developed in my group at UCLA, and these pictures here give you a little bit of idea how we operate this. Basically what it is a small telescope, for these type of measurements the size actually doesn't matter, that is able to scan both in azimuth and in elevation. And so what we do is we basically look into the basin in the limb, so at 0 degree elevation, a little bit above, and you can see one arrow here that also looks into zenith. This is our solar zenith angle. We're scanning over 6 to 7 elevations and also in different azimuths. I'm really only going to talk about the elevation scans because I think a lot of the interesting information is in the vertical profiles. So I'm going to focus on this. We have a cycle length of about 60 to 80 minutes. We're doing actually 2 different wavelength ranges with this system. So, and this is about the repetition rate that we get for these scans. Now, I want to very briefly explain how we do this, and this is important to understand the MAX-DOAS data, but also a little to give you an introduction for the near-FTIR system, because the problems are very similar. So what we basically do, we measure light reflected from the surface, solar light reflected from the surface or the atmosphere, and we're basically measuring that light as it enters the instrument. And then we're using the trace gas absorption, so the absorption bands, which are like a fingerprint for all these trace gases, to quantify the integrated amount of trace gas along that path through the atmosphere. And we call this integrated amount the slant column density, or the column density in the case of the UV, but it's the same idea in the FTIR, that it's a path integrated measurement. For the UV, we actually have to measure a solar spectrum to do our data analysis. So when I talk about differential slant column density, then it's the comparison of the downward looking measurement to the one into the zenith. That serves 2 purposes. Number one, we need to take out the spectral structure of the sun, which is very strong in the UV and the visible. And the other one, it takes out a stratospheric signal. For trace gases like NO2, there's a very strong stratospheric signal, which we would have to subtract out. So we regularly look into the zenith, and then we look down to correct this. And so the initial data I'm going to show you are differential slant column densities, and I'll explain a little bit how we can convert this into something that is more understandable, meaning concentration and vertical profiles. So we do this data analysis, and I always like to show at least a few atmospheric spectra. What you see at the bottom are three of the species we analyzed. The first one is NO2, which is is one of the ozone precursors in the LA Basin. The right one is formaldehyde, which is actually quite interesting, as I'm going to show you later. And the one on the left here is actually O4. It's the oxygen oxygen-oxygen collisional complex in the atmosphere. And this for us is a tracer for radiative transfer. So it depends on the path length. O4 has a constant concentration profile in the atmosphere. So if its signal varies, it's only due to the change in the path length in the atmosphere. So for us, it's a way of determining how we look through the atmosphere. I should mention that this idea of using a tracer for the transfer of solar radiation in the atmosphere is also something that will come in the FTIR, except they're using directly O2. We can't in the UV-Vis because there's no O2 absorption, so we use O4. But having this tracer for the radiative transfer is very important. Now we can analyze these gases in different wavelength ranges, and I'm only going to talk about the one in the UV. It's going to become obvious a little bit later why. So we can see these differential slant column densities, these path average absorptions, but the next step really to get to these concentrations is to understand what determines the path length in the atmosphere. So you need to do a little bit of a consideration of this transfer. And this figure here shows different events in the atmosphere that impact how the path looks through the atmosphere. The first one is fairly straightforward. This is this point A here. In many times what we see is sunlight reflected from the surface. If this would be the only source of light, our life would be a lot easier. Unfortunately, there's other events in the atmosphere that also provide a path for the photon into our instrument. The first one is scattering by air molecules, which is also something that is relatively easy to take care of. But the next one is scattering by aerosol particles, and that obviously, as the aerosol particle concentration in the LA Basin is highly variable, is hard to easily to determine. But that at high, you can just imagine that a very strong haze, you may not be able to see the surface. So your entire light actually comes from the atmosphere, and you have to determine what that path actually is. So that's a major challenge. You can also have events where photons get scattered twice, which makes it even more difficult. So this is the biggest challenge for the UV-Vis measurements. It's a lot easier for the infrared because Rayleigh scattering is much, much smaller because it's wavelengths dependent. And also Mie scattering is much smaller. So in the IR, as you're going to see later, you can use oxygen to scale your radiative transfer. Unfortunately, you can't do this in the UV visible. So one of the things we need to do is we need to perform radiative transfer calculations. So we have an extra model that does nothing else than simulate how the light propagates through the atmosphere. So then the question is, with all these difficulties, is how we get concentrations out of this. So these are fully automated instruments, at the MAX-DOAS is, so normally nobody is there. So one of the big challenges that we have to figure out first is that we have clouds. And you may have heard this from satellite data. They have cloud sorting algorithms. We think satellites have it easy because they know all the clouds are below them. We at Mount Wilson cannot say this because we can have clouds below us and above us. So we have developed a number of cloud sorting algorithms to, at the moment, throw out the data that is contaminated by clouds. The FTIR does something very similar to what we are doing. We're using both the intensity that we collect as well as the signal by O4 and the FTIR O2 to basically identify measurements that have clouds in them. So when you're going to see data sets that have gaps, then these are typically gaps where we have cloud coverage. And you may think about LA as the place where the sun always shines. It's surprisingly cloudy in LA. We often have stratus decks, and we also have high clouds. So the data set by itself has gaps whenever there is clouds around. So let's go back to the radiative transfer. So what we're doing with the MAX-DOAS system is we're basically scanning, looking at different altitudes. So one of the things that we looked at first and that we need to understand is qualitatively how sensitive are these measurements when we look at different angles to different parts of the atmosphere. So what I'm going to show you is a little animation, not animation, but a few slides that give you an idea how the sensitivity varies with viewing angle. So the first thing you see here in this plot is the altitude of Mount Wilson. Mount Wilson is about at 1.7 kilometers altitude. The x-axis is what we call a differential box air mass factor, which basically gives you the contribution of this layer of the atmosphere to the measurement at a certain elevation angle. So I went one too fast. So in this part, we're looking at the 0 degree, the limb measurement. So we're basically looking parallel to the ground out from Mount Wilson, and without anybody's surprise, we're mostly sensitive to the altitude at Mount Wilson. This is actually the viewing angle where, on a concentration basis, we're the most sensitive to the concentrations. The very long path lengths, we're very sensitive to this. So what happens if we look down into the atmosphere? And what you see here is that as we look down, the amount of absorption that originates from lower in the atmosphere goes up the further we look down. Now this is a little bit a skewed picture. This is just a sensitivity. It turns out because there's so much more of pollutants like formaldehyde and NO2 near the surface in the boundary layer, the sensitivity is actually much stronger than this implies. But as we look down, we get more and more sensitive to the lower part of the atmosphere. Now we also look up, and if we look up above the limb, then we're mostly sensitive to the area above this, above Mount Wilson. So we can use this dependence on the viewing elevation angle to actually retrieve vertical profiles for NO2. And the way we do this is basically a two-step process. We need to first understand how light gets transferred in the atmosphere. And we have two ways of doing this. One way is we can use the radiative transfer model with our O4 measurements in the nonlinear optimization process to actually derive it from the O4 measurements. Or we can use external data like the Aeronet station that we're operating at Caltech and some LiDAR observation that gives us boundary layer height to constrain it that way. Once we know the radiative transfer, which is mostly dominated by the aerosol extinction profile, and we have the trace gas observations at different elevation angles from the MAX-DOAS, we can put this in the radiative transfer model and do an inversion. And this inversion then gives us vertical concentration profiles, and it also gives us information on where we're sensitive to. It probably isn't too much of a surprise if you have very hazy atmosphere, you're not sensitive to the surface because you just cannot see down to the surface. So this information is also provided to us and it serves as a quality measure. So the first thing we did actually is a question that I'm going to go very briefly. We did some theoretical calculations to actually determine under different situations how much information can we actually get in the vertical. I mean, it doesn't help us to scan if in the end we can only get one piece of information for vertical profile because then we can only measure one concentration. So we went through a whole bunch of sensitivity calculation, and it turns out that for NO2 we can get about 4 to 5 pieces of individual information. So meaning any profile has about 5 real concentration points in it. Even though there's more concentration points when I'm plotting them, the real information is only about 5. But that's actually quite good for such a system, and it definitely allows you, as I'm going to show you now, to distinguish in boundary layer concentration to concentrations above the boundary layer, which is the one thing that in the end we really want to understand. So what you see here is actually 2 of these profiles, just as an example that we determined. This here has a boundary layer of about 750 meters and about a concentration of about 10 ppb in the boundary layer. And then you see the concentration drops up very quickly as we go above the boundary layer. The one on the right, which is taken a few weeks later, actually has a much lower boundary layer of about 500, a much higher concentration, which is just pretty much what you expect happens in the LA atmosphere, that the concentration or mixing ratio changes with boundary layer height. So you can take this data set and ask yourself, how good is it? Is it actually useful? So what we did is, for a 3-week period, we took only the lowest mixing ratio that we retrieved, so the lowest 100 meters in our retrieval, and compared this to the Azusa ground station for NO2. And the comparison here is the red dots are the MAX-DOAS lowest 100 meter averages, and the Azusa station actually shows that we're doing a fairly good job in retrieving mixing ratios at the surface. We capture all these events, we get the low concentrations here fairly right. So that's actually quite encouraging. And do remember, this is the hardest part, is retrieving surface mixing ratios for us, because we're getting less and less sensitive the more polluted it is. So when you take this data set, you can, for example, go and look at some of these days and plot them in kind of a fashion way that gives you a two-dimensional view of what really happens throughout the day. So these are several days. We don't measure at night because we need sunlight, so the white areas is the nighttime. But you can see, for example, here on the 16th or 15th, these are in UTC, you see this growth of the boundary layer as we go up and filling up the boundary layer with NO2 as the day progresses. But then we have days like the previous day where you actually, we must have seen a plume near the surface. This is one of the days where Azusa also saw these very, very high NO2 levels. So we have these this two-dimensional information that we can use. So this gives you a really nice data set of altitude-resolved NO2 concentrations that then you can compare to a model, which is something we're still working on. I want to switch gear a little bit because this, as you probably realize, is a lot of mathematical effort to get to these profiles. So one of the ideas that came while we were doing this is that there may be an easier way to actually learn something about ozone chemistry that doesn't require that much math and you can do really quickly. And this is based on an idea that Sandy Silman proposed in the 1990s, where you can use certain ratios of traces or ratios of parameters to understand the sensitivity of ozone formation to NOx or VOCs. And many of you probably know these isopleth plots that show you ozone production dependent on VOC emissions and NOx emissions. And the chemistry basically of ozone formation is controlled by the NOx levels. If you have very low NOx levels, your ozone formation is pretty much proportional to the NOx levels. Often then, because the main loss is actually not the NO2 reaction with OH, but the self-reactions or other reactions. If you increase NO2, you go to a level where the high levels of NO2 reduce your ozone formation. So we distinguish these two areas as the NOx-limited and the VOC-limited areas. And one of the questions that always comes up is, in what regime are we currently in any area, and does it change as we change emissions? So Silman came up with this idea of using the loss of NOx compared to the production of radicals to put a limit to these VOC-limited and NOx-limited regimes. And his quantity is called ln, so it's the loss of NOx over the radical formation rate. And if lnq is larger than 0.5, it's VOC-limited, and if lnq is smaller than 0.5, then it's NOx-limited. So how can we use this to actually learn something from our Mount Wilson measurements? Well, it turns out that formaldehyde actually provides also a measure of your radical levels or radical formation levels. So what you see here is a measurement or calculation based on OH and HO2 measurements and NOx measurements from the CalNex field experiment, where on the left axis you see this ln over q parameter. I have to be careful with this. And on the bottom, you see the in situ formaldehyde to NO2 ratio. And you see there is not a linear correlation, but there is a very clear relation between the two. So what we did is we used this data, which is specifically for Los Angeles, and just looked where is this turnover point when we look at formaldehyde to NO2 ratios. And it turns out that that ratio, if it's below 0.55, it's VOC limited. If it's above 0.55, it's NOx limited. So now we can go back to our data set and really look directly into the data. And because we can derive formaldehyde and NO2 in the same wavelength range, so they both have the same path through the atmosphere, we can directly use our measurements. We don't have to do much calculations. And so to show you a little bit that this works, this is the CalNex period, and the gray bars are the weekends. And you see the formaldehyde to NO2 ratio from the MAX-DOAS measurements at looking down into the basin and just looking in the limb. And what you see is that a clear change between weekdays and weekends in the ozone sensitivity, which is something we've been talking about for quite a few years. We typically are below the crossover point at this point. So we went and said, well, we have a long data set. Can we learn something about this formaldehyde to NO2 ratio over a multi-year period? So we went back and did something similar. So we looked at this ratio throughout the year. And what you see here is in red are weekends and in blue are weekdays. And what you see is, just looking at the lower graph here, that when you look down into the basin, throughout the year there's a difference between weekdays and weekend, and then there is a seasonal variation. I have to say we don't know exactly why there is a seasonal variation in this ratio. It could be because there is less sunlight, so less radical activity in the winter. It could also be that just the VOC emissions in the basins are lower in the winter. There may be a change in metrology. This is something we're still trying to understand where this is. But one thing we can do is we can actually ask ourselves, is this variation coming from the NOx or coming from the formaldehyde? And so we went and took just 1 year of data, downward looking into the basin, and just plotted took the hourly averages of the slant column densities and plotted them weekend versus weekday. And what you see is that on the right, the formaldehyde DSCDs, they match perfectly on top of each other. The arrow bars give you the variation that really happens throughout this averaging period. When you look at the NO2, you see a very clear difference with much higher NO2 slant column densities during the weekdays than during the weekends. So this is actually very simple for us to do because we basically just need to do the spectral analysis and calculate this, this ratio. So it gives you a pretty much very quick way of following the ozone sensitivity over long time periods. So let me switch gear now and talk about the greenhouse gas measurements, which were done by Stan Sanders' group from JPL. And our interest obviously is both in CO2 and methane, which are the two strongest greenhouse gases. And for CO2, we know that the emissions are primarily from fossil fuel combustion, traffic, and power plants. And those emissions are probably fairly well understood, maybe to within 10%. There is actually high-resolution emission inventories that are available in the science community. The picture is a little bit different for methane. So methane is the second most important greenhouse gas. On a per molecule basis, it's about 25 times more effective than CO2 as a greenhouse gas. And it comes from a variety of sources that are not necessarily linked or not really linked to CO2. So some of these sources are, for example, landfills. It's a very strong source. Dairy farms. There is the big unknown, which is pipeline leakage. There is a huge network of pipelines in the LA Basin. And there's a little bit of emissions from wastewater treatment plants. So because of this mix of different sources and many of those area sources, there is actually fairly large uncertainty in the methane emission inventory for the LA Basin. So there's obviously a need to really work on these to provide better estimates for the emission inventories. So what Stan and his group did is they developed this Fourier Transform Absorption Spectrometer that works in the near IR. So it uses the same principle. We're looking at scattered sunlight, mostly from the surface. And this is a little slide that shows you this spectrometer is actually located inside the trailer, and there is a pointing optics in the dome. It can be scanned both in azimuth and elevation. So there's two measurement modes that are done with this. The first one is looking at a diffuse target. It's basically a big white Teflon plate, a little bit fancier, but that's what it is, where you look directly at the height of Mount Wilson, and that gives you the absorption column from Mount Wilson up to the sun. So you get the free troposphere, stratospheric, averaged CO2 and methane concentration, which gives you an idea of the background above Mount Wilson. And then you can also look down into the basin and then scan different areas. So the instrument measures CO2, methane. It also measures N2O, CO, and O2. And O2 is actually used afterwards to correct for radiative transfer effects. So the viewing strategy of this instrument is a little bit different than that of the MAX-DOAS for a number of reasons. One of the reasons is that it's much more sensitive to the reflection on the surface than the MAX-DOAS. So what Stan's group did, they selected 28 reflection points, and reflection points are points that show fairly high and throughout the day constant reflectivities. That's important to maintain a good data set. So, and these reflection points are distributed fairly equally throughout the basin. And then the instrument cycles 5 to 8 times throughout the day, aiming at each of these reflection points, and also 4 times to the Teflon plate, the spectralon plate, to get the column above Mount Wilson. And that gives you a fairly unique area view of greenhouse gas concentrations in the basin. I should remind you, these are path-integrated measurements. So basically, you measure along a line from Mount Wilson to that reflection point. So it's a real average. It averages both in height, which is actually an advantage because you're crossing the entire boundary layer. So you're not sensitive to boundary layer height. And it also measures in the horizontal, which makes you fairly insensitive to point sources. So you can then look at some of this data, and what is shown here is excess CO2. What this basically is, you take the CO2 column measurement and you divide it by the O2 column measurements. The two are in pretty much the same wavelength range. So they have both the same radiative transfer through the atmosphere. And then you scale it with the mixing ratio of O2 to get basically a greenhouse gas mixing ratio that is corrected for the radiative transfer effect. So effects where this is not just a geometric line. The effects are much, much smaller for the FTIR. So doing this, it doesn't introduce a large error, but it guarantees you that you're not really sensitive to this. And what you see is 2 things. On the top graph, you see X CO2, and at the bottom, X methane. If you just look above Mount Wilson, you see that the CO2 and the methane excess mixing ratios are actually fairly constant throughout the day, which is what you would expect for a greenhouse gas that basically air that traveled over the Pacific for weeks and just arrives over Mount Wilson. You get the concentrations that you would pretty much expect. This is for 2012, so I guess we're still at 390 ppm for CO2. And you see about 1750 ppb for methane. Now, if you look down into the basin, you actually see, number one, much higher levels, which is not surprising to anybody because the sources are all down at the surface. And you see a diurnal variation. And you can think about this, the morning is really kind of the buildup of these emissions in the boundary layer. So you start accumulating both CO2 and methane. And then in the afternoon, typically in LA, the winds really pick up at noon. So that decrease afternoon is most likely just advection of the pollution, where some of the high pollution is transported to the eastern part of the basin. So the question is, it's obviously, what can you do with this data? So one of the first things you can do is you can see how the excess methane and excess CO2 correlate to each other. That gives you a little bit of an idea that, or this allows you to take out these transport processes to a certain extent, advection. And what you see is that there's a very tight correlation between methane and CO2. So you can interpret this that the slope gives you a measure for the relative emission fluxes of these greenhouse gases in the LA basin. You can then look and project these calculations for each of these targets point onto a map in the LA basin, and what you see is that this slope, so this ratio of excess methane over excess CO2, and this is expressed in units in ppb over ppm, varies inside the basin from about 5.4 to about 7.3. This is just the observations. One of the things that SANS group's working on is really trying to also compare this to a model, and I'll get back to this later and how these ratios vary throughout the basin, what the implications are for the emission rates. So the obvious question is, can you derive a flux for methane in the LA basin? And what SANS group did is that they linked the methane to the methane emission rate to the much better known CO2 emission rate. And this is now for the entire LA basin. Now remember, the system really scans the entire basin. I mean, you've seen where these reflection points are. So we're really looking at a basin-wide average. And So the CO2 emissions come from a highly resolved database. And so you use basically this ratio that I just showed you and multiply this with molecular weights, and then you can determine your methane emission rate to about 0.39 teragrams per year with an error of about 0.06. And that error mostly comes from the uncertainty in the CO2 emission inventory. So if you look at the literature, you can see that this value actually agrees fairly well with some of the more recent data, for example, the CalNex measurements, some of the in situ measurements done at Caltech, as well as the ones that the ARB is performing at Mount Wilson. They're all about the same range of 0.37 to 0.41, which is within the uncertainty. So these measurements are fairly consistent with these other determinations. So one of the interesting things that comes out of this, if you go and take the long-term data sets, this is several years now, I think this is 4 years, and really look at the monthly distribution of these ratios, you see that there's actually a spatial variation in the basin. And that is something that still is under work to understand, but one of the interesting parts is that, for example, you see here in the eastern part of the basin in July, August, September, very large ratios. So there is variation in these emission rates throughout the basin, even with this path averaging technique. So don't remember, these are not in situ techniques. So the averaging path can be sometimes between 4 and 40 kilometers. So very, very large areas. So you see this variation. So one thing you can do to look at this from a temporal point of view is you can just look at this Fourier data set and just do monthly averages of the basin-wide ratios. And you see that there's 2 peaks basically that regularly show up. One of them is in this July, August, September area. And the other one actually is in winter. And the hypothesis right now, let me put it this way, is that the winter peak actually likely comes from the increased use of natural gas, because it does get cold in LA and we do heat our homes. So in winter time you use a lot more natural gas, and there's kind of a theory that the late summer peak comes maybe from biogenic activity that may be related to temperature, although that is still something that needs to be investigated. The variation of the methane to CO2 ratio is about 20 to 28% throughout a year. You can do the same calculation where you actually take a monthly resolved CO2 emission database and calculate the emission rates, and you see the methane emission rates show the same variability. So that's something that's still work in progress in trying to understand how to explain these variations. You can look at the annual trends of the basin-wide methane emission rates. The gray areas is what the CLARS-FTS determined for the different years. And there is very little variability in the methane emission rates from year to year, or there's also no trend. And the values, this is in gigatons per year, is about 380, 390. And the blue bars is the apportioned carb emission rate, basically taking the statewide methane emission rate and subtracting agriculture, because we don't do a lot of agriculture in LA, and then scaling it with population. And that is considerably lower than the methane emission rate determined by the Fourier transfer. So there is a significant difference between the bottom-up and top-down emission inventories that I guess at some point need to be reconciled. If you read the newspapers, you know that there is this very big leak near Porter Ranch, which is a natural gas storage unit that has been found to leak. So CLAIR actually looked into that data and decided to provide you a view of what this looks like from the CLARS-FTS. So on the left you see a graph from the end of September this year. And you see these ratios in this figure are 5 to 8 ppb to ppm, so methane to CO2 emission rates. And on the right you see the measurement a month later. And these ratios have doubled basically. And this is mostly in the western side of the basin. And the red star here actually shows you the source of that leak. So the CLARS-FTS actually doesn't look towards the leak. So what you're seeing is basically the advection of this very, very large methane plume into that viewing area of the CLARS-FTS. So there has to be some more analysis to see if you can actually extract quantitative information from this. That may be a lot more difficult than one may think. But the leak clearly shows up in the data, and these ratios that are observed at the end of October are larger than anything else that the CLARS-FTS and Stan's group have seen in the years before. So let me give you some conclusions from our project. First of all, we developed 2 remote sensing tools, and I really hope I have convinced you that these tools are very useful and provide information that you can't really get otherwise. I mean, we can measure vertical concentration profiles for NO2, so you get both boundary layer height basically and the average concentration as well as concentrations above. That would be very useful to actually either incorporate or compare to an air quality model. We can, which I personally is one of the things that I'm excited about, provide information from a measurement that you usually don't think about. We tend to think about concentrations, but with this ratio of formaldehyde to NO2, we actually get direct information of the chemical system that drives ozone pollution in the LA basin. And that's a measurement that is surprisingly easy to make for us, and could be quite useful when comparing to a model to see if the model actually captures the sensitivity to VOCs and NOx correctly. Then obviously one of the quantitative really interesting results is Stan's emission rate, annual emission data for methane, which is in this 0.39 plus minus 0.06 teragrams methane per year. And as I mentioned earlier, this is higher than the ARB currently. Well, if you take the statewide emission inventory and scale it, it's higher than that value. Should be a little bit careful since there isn't the specific methane emission product for the basin. And there is a spatial and temporal variation in the basin that is quite interesting and requires some more investigation. And then CLARS really, because for example the MAX-DOAS system is a fully automated system. I mean, we don't go there more than every few months. And the FTIR is also at this point fairly automated. It provides a really good way of performing these long-term measurements of either major pollution events such as tracking emissions or looking how the chemical system changes. And that includes the gas leak I showed you. Also interesting, we could look at wildfires, refinery leaks, and others. As with any research project, there is always more work to do. For the MAX-DOAS, one of the things we're still working on optimizing is the aerosol extinction profiles. I didn't have time to talk about this, but that's obviously also of major interest since particles are another major pollutant. We're still trying to understand that seasonal cycle of the formaldehyde to NO2 ratio. So we're trying to either build small models or work with somebody who actually runs a 3D model throughout an entire year. And these are often not scientists because we tend to look at a few days, but not at an entire annual cycle. One of the issues for the CLARS-FTS is trying to understand these methane seasonal variations in the methane emission rates, as well as the role of transport and inhomogeneous emissions in the LA basin. And the goal with this is really combining these CLARS observations with a model to give more quantitative information of the spatial and temporal distribution in the basin. And with this, I'd like to thank you for your attention and acknowledge 2 people who have helped with the project, Vijay Natrai from Caltech, who helped us with the radiative transfer methods, and Steve Herlock at UCLA, who built the instrument, and then also funding from the ARB, NOAA, NASA, and JPL, which maintains the CLARS Observatory. Thank you.
Thank you for the great presentation. My name is Kathleen Kazawa, ARB. Thank you for giving us the preview of the Aliso Canyon leak. That was my question when I first was recognizing what the project was about. But is this going to be part of the report? I don't know if that will be, or this will be a separate study that...
No, that's a separate study. I mean, we finished the project, so the project was done before, but Stan is continuing these measurements. And I know they want to look into this event more. The challenge will be to get quantitative information out of this because it's a point source. To really get fluxes out of it, you kind of have to co-emit CO2 from the same point source. And I don't think that leak emitted any CO2. But this is only, what, a month and a half ago? So I think it would be really interesting to explore if you can use this observation to look at leaks or single point source emission rates.
Hi, Darmams, ARB. And you have a very unique setup with the Mount Wilson Laboratory. Is this technology transferable to other locations in California, or are you just going to be restricted to the South Coast Air Basin?
Well, you need a mountain or something high up, but there are places where you can do this. Otherwise, I don't see that should work anywhere if you can set up an instrument. Now, MAX-DOAS systems are fairly portable. They're much smaller. The FTS is a little bit larger. So I think there is only kind of logistic problems. This would be the only challenge because you do have to put a container up and provide power. But there is nothing that keeps you from doing this in other places as long as you have a mountain.
One more follow-up since I still have the microphone. Have you done any comparison with ceilometers or anything like that?
With ceilometers?
Yes.
Yes, we have looked at kind of the boundary layer heights for the vertical profile retrievals, right? Yeah, and we seem to be getting these boundary layer heights and the growth pretty well. I mean, if you've looked at in situ vertical profiles of NO2, for example, from the aircraft at CalNex, you see that there is really a kind of a step function when you hit the boundary layer. I mean, it's a very clear limit. So within the resolution that we have, which is in this case about 100 to 200 meters, yeah, we can determine where the boundary layer is and look at that growth of the boundary layer.
Thank you.
Okay, well, we're waiting for an email question. Hey, nobody told me, so I need my glasses. Okay, I'm going to read the question so that everybody can see. How specific to the LA Basin is your conclusion as to using this ratio to determine VOC or NOx limited conditions? Might it be applicable to other metropolitan areas? Yeah, I think so. I think there are some studies from using satellite measurements, OMI and GOM satellite measurements, that you can do this. I think what I've shown you is actually the models always do it. What I've shown you is actually they can see it from the field data. So I think this is universally applicable. What I don't exactly know how that transition point varies from location to location, as I don't know how it varies from season to season. So that requires good model calculations, maybe model calculations with a mechanism that is a little bit more sophisticated than what's in an airshed model. But from the basic chemistry, this should always work. And these Silman factors have been used in the kind of science community, folks that go out and measure ozone chemistry or study ozone chemistry with observations, they have been used for quite a while to understand ozone sensitivity. So I think it should be applicable to most places.
Steve Gouget, Air Resources Board. Could this technology be used to look at ozone in the vertical?
Well, it is used for ozone in the vertical. This kind of differential absorption is the basics of all satellite instruments. The problem is usually if you want to use it in the troposphere, you have to separate out the stratosphere. And the stratospheric signal, when you look into the sky, is much, much larger than the tropospheric signal. So yes, you can do it. When you actually do the calculation, you introduce such a large uncertainty because you're subtracting two large values from each other. And that's why I'm not aware of anybody really having done that. So it's mostly an uncertainty problem in the end.
Hi, this is Kevin Essinger from the Air Resources Board. I just actually have a curiosity with the weekday weekend formaldehyde NO2. I would be really interested to see Monday through Sunday single day analysis instead of just chunking weekdays and weekends together, because LA actually has very interesting traffic patterns with really light Friday morning and then heavy Friday evening, and there is a different day by day kind of analysis which would show greater. Is it a NO2 role?
NO2, yeah. Yeah, it's a good idea. We haven't done it yet. I mean, but yeah, I mean, we have plenty of data to do the averaging on a per day basis. I mean, it's like 3.5, 4 years of data. So yeah, that's you're right. I mean, there is a difference between weekdays too.
Hello. I'd like to thank Jochen again for dropping by here and giving a wonderful seminar about his work and Stan Sanders' work on Mount Wilson. Thank you again.